When you hear the word crystal, what comes to your mind? Shiny, luxury. But what image comes to your mind? What image comes to your mind? Something like what? Edges, like sharp thing, right? Sort of something like this, I think. Like this, right? Okay. So this, yes, this is crystal. The peculiar thing about crystal is that if you look at this, what we call this edge, the surface is very flat, and it also has sort of like hexagonal pattern, hexagonal shape like that. So the thing that you should know is that this pattern, this hexagonal pattern, the flat surface, is not happen due to because people cut it. It happened naturally. So the crystal grow like this. Okay. When you see a diamond, like this thing, this people cut it. Okay, it's not occur naturally like this. Okay, the reason why people cut the diamond in such a way because this is raw diamond. There are no shape like this. The raw diamond is just like a cube or what, like sort of like that lah. But people cut it like this because why? Because diamond have high refractive index. We learned in FTIR before the ATR crystal. Normally they use diamond because diamond have high refractive index, meaning that when you shine the light can reflect inside the diamond. So if you shine the light here, the light can reflect inside the diamond. Normally when something transparent, they go straight, right? So that's what we mean that high refractive index. It can have this total internal reflection. They can reflect the light inside the material itself. Total internal reflection. So people cut diamond like this in order to maximize the total internal reflection so that when you shine the light to the diamond will glow brilliantly. Okay? But the raw diamond is like that. Okay? Compare with the quartz, compare with the crystal like this. This is what we call quartz. Quartz. This, no one cut like this. It's occur naturally. Okay? So inside this, okay, inside this what we call, inside this thing, there are silicon. This is quartz. Inside quartz, there are silicon and oxygen. There are silicon and also oxygen atom. And the silicon and oxygen atom inside this quartz, they arrange sort of like have pattern. They are pattern for this arranged inside this thing. So we call this quartz as crystalline material. Okay? Crystalline material, the definition of crystalline material. Crystalline material is basically a material that is a material that the material which its constituent either the atom or molecule or the ions. I'm not sure which is constituent material. Arrange in highly ordered manner. We call it, we have name for this. When something arranged in highly periodic manner, we call it periodic. Over large atomic distance. So we can see also they have what we call long range order exists. Okay, so this is the definition of crystalline material. A material which have its constituent, whether it's atom, molecule, or ions, arranged in highly ordered manner. Okay, we call it periodic lah. Over large atomic distance, or in other words, long range order exists. So this silicon and oxygen, they sort of like periodically arranged inside this thing. Okay. The opposite for crystalline material, we call it amorphous. Amorphous. The opposite for this amorphous material, where the long range order didn't exist. Long range order didn't exist. exist. Hopefully at the back you can see. You can see? At the back, cannot see? They are always, they are like empty, 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 empty. So you can come in front if you cannot see. Okay. So that's the thing. So in quartz, in silica here, in quartz here, the silicon and oxygen here, they call it here in quartz. If I put quartz here, quartz, they have silicon and also oxygen. They are also a material that have contained silicon and oxygen, but it's amorphous. That is glass. If you see here, they are glass. They also have silicon and oxygen inside the material. Okay, but inside the glass, the silicon and oxygen doesn't have pattern. In quartz, like this, they have sort of like a pattern. So silicon and oxygen in quartz or in glass, we have a name for it. We call it silica. We call it silica. Normally, we call it silica. Silica. Or its empirical formula is SiO2. Okay, silicon dioxide. So this is another name for the quartz and glass, silica or silicon dioxide. Okay. If you look here, if you look what we call here, so this is an example of the atomic arrangement of silicon and oxygen inside the quartz. This inside the glass. The red one here is oxygen. The blue one here is the silicon. Basically, this is quite wrong because the silicon is bigger than the oxygen because silicon atomic number is higher than the oxygen. But just for the sake of showing the arrangement, that doesn't matter . But here the red one is oxygen, this one is the silicon. This is also the same. So you can see the difference between crystalline and non-crystalline material. We call it amorphous, we call it crystalline material. So if you look here, one silicon atom here connected to 3. 1, 2, 3 oxygen. But here they are silicon O2. Why they are O2 here? Why here there are 3 oxygen? Why not it's silicon O3? Okay. First off, this is 2 dimension. If you look in 3 dimension, there are another silicon. Let's look at another dimension of this quartz in 3 dimension. So this is where I ask you to for the what you call the install this VESTA. So you can see the VESTA is visualization for electronic and structural analysis. Basically, this program is a free open source software. So normally it's used to visualize the crystalline material. You can draw the material by going to file, new structure, and then it gives this. And then let's say you want to sort of like unit cell. Let's say you just go. Let's say you want to put instead you want to put the oxygen symbol. You go to the oxygen, and then what will happen if you click OK? You can see something like this. Okay. So basically, this software is allow you to sort of like visualize things in 3 dimensions. You can play around. Normally, it's difficult when you read the book. When it's not 3 dimensions, it's difficult to sort of like make your mind how this look if you rotate like this and that. So this is one of the software that you can use . So it's same also with the ChemSketch. I believe in organic chemistry, Dr. Munira asked you to install ChemSketch, right? And learn about that. ChemSketch also, you can go for the 3D. There are ChemSketch 3D, but you need to render and so on. And in ChemSketch, when you draw like 1, you only get, in 3D, you get only 1 atom . But here, just now, if you look how I did, I just put the O, right, oxygen, and then it gives 4. So it's sort of like more focused on crystalline material because this is one of the unit cell of crystal . So I will talk about unit cell later on, but just to show you that this software, it is your ways to what you call, to learn in 3 dimensions. Okay, so now I can sort of like create the what we call silicon dioxide, generate the silicon dioxide pattern in 3D here. But the problem is you need to know all this arrangement and so on. So that's why there are easy ways to do that. So how to do that is that you go to what we call this Crystallography Open Database. You Google Crystallography Open Database. You can go and click this COD. Hopefully the internet is okay. So basically this the open database, they sort of like they curate all the crystalline material. Okay, so Crystallography Open Database. So how to use this thing is just give you the basic idea. Just go to search. Just go to search, and then if you look here, they ask you how many elements you want to put. We want to see the silicon and oxygen in quartz. So we put silicon and oxygen. So we put Si, and then we put oxygen there. Okay, and then you have this thing. If I just put the element here and I send, meaning that I make a query. So I send this thing. What will happen is that they will try to find all the publication that have silicon and oxygen plus other thing. Silicon here, you have silicon 2, oxygen 6, plus other thing, plus other thing. We don't want this. We want only silicon and oxygen. So how to do that? You go back, and you make a constraint. So here, number of distinct elements, minimum and maximum. What is the minimum number that we want? We want the minimum number, they must be 2, silicon or oxygen. So we put 2 here. We put 2 here, and also the maximum number. What is the maximum number that element that you should have inside this structure that you want to query? 2 lah, because we don't want other thing other than silicon and oxygen. So we put 2, okay, and then we send again. So here now the difference between before is that they will sort of like list down all the silicon and oxygen only, silicon, oxygen, and so on. So this is all what we call the journal, the paper. Normally when people do the research, they in crystallography field, they find a new structure and then they record the structure in the journal and then they make it public, the structure itself. For example here, let's say we want to see the quartz structure. So let's say we can go to, where we want to go? Let's say I want to go here, this thing. Let's say we want to go here, this thing. Die Bindung in Quartz, this is in German, binding in quartz. So let's say I select this thing, and then, so if you look here, there are CIF. CIF stands for Crystallography Information File. So if you click this, you will download the file. So if I click that thing, they will download the file there, and then I go to the VESTA, and then I go to File, and then I open. And then when I open, let's say this is the one that I download. So let's say I rename this to what we call rename to quartz. Quartz. Okay, enter, and then I open this thing. So basically what will happen, this is structure coming from the file, CIF file, the Crystallography Open Database. So this is a quartz. Okay, what happened inside the thing? You might not see like this. If you look here, it's nothing like this, right? Because this is in 2 dimensions. What you see just now is in 3D. That's why when you go from 2D to 3D, it's quite like haywire lah. You need to play around, something like this. The best way to learn about 3D dimension is that to build the model by yourself, by your hand. Remember previously you see in the old school, they use the model, ball on stick model. That is actually the best way to learn about 3D. This is the second best. The best way is that you build yourself, okay? Because when you just read from the book, it's difficult to think. So this is the quartz. So you can see something like that, okay? If let's say I want, so this is 1 unit cell, okay, 1 pattern. If I want to make this more pattern, so I just go to the boundary here. Go boundary, let's say I put 3, 3, 3. What does it mean when I put 3, 3, 3? So this is the boundary here, the boundary. What does it mean? I put 3, 3, 3. I will put another 3 here, 3 top, 3 bottom. Okay, so what will happen? You give something like that. Okay, so instead of you try to generate by yourself one by one, so just using this thing is much easier. Okay, so now still nothing look like what you see here, right? So that's the difficulty of 3D. Not difficulty, I mean that's the beauty of 3D. It's 3 dimension. This 2 dimension, it's easy, right? But if you look, what I want to show now, let's say I go to boundary first, because this is quite messy. So let me put 1, 1, 1, 1, and enter, apply. Okay, if you look here, one silicon atom, silicon is in blue, one silicon atom attached to 4, 1, 2, 3, 4. One silicon, 1, 2, 3, 4. You might not see very clearly here. Let's go to what you call the polyhedral. Now you can see quite clearly lah. Okay, so in the middle here, there are silicon atom, this oxygen. So the connection is like methane that we learned before. It's tetrahedral. So it's like a pyramid. So you have the silicon atom at the middle, and then you have the oxygen atom in the side. So this is the thing. Okay, so here the question is why, if the silicon connected to 4, why then here we call it silicon dioxide? Why not silicon 04, silicon dioxide? The reason for that is that because this is empirical formula. What does it mean by this? If there are 100 silicon, there will be 200 oxygen. It tells nothing about the what we call the bonding. Because if you look silicon, if you look this PT table, if you look at the PT table here, if I open the PT table, silicon and oxygen, silicon, if you look silicon here, silicon, where is silicon? Silicon here. So silicon have what we call the 4 valence electron. So if I draw silicon here, so silicon have 4 valence electron. 1, 2, 3, 4. 4 valence electron. And oxygen have how much? Oxygen have 6 valence electron. 6 valence electron. So oxygen have 6 valence electron. 1, 2, 3, 4, 5, 6. Okay. So in order to make octet, they can make like this: oxygen, 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 oxygen. So they have like, so you can make octet. You can revise back lah the how the bonding covalent thing. But you can make like this, or you can make like this. Okay, you can make like this. Okay, both are valid. Okay, both are valid. But this is more stable. It's more favorable. That's why you can see in the 3D dimension, the silicon and oxygen sort of like binding with the what we call with the 4 oxygen. Remember, when you heard the word silicon dioxide, it tells nothing about the bonding. It's like when you learned before, nitrogen, oxygen 2, and also chlorine 2. You know there are 2 nitrogen, 2 oxygen, 2 chlorine. But for nitrogen, you have 3 bonds. For nitrogen, you have 3 bonds. Oxygen, you have 2 bonds. Chlorine, you have 1 bond. So this is just empirical formula. When you learn in organic chemistry, this empirical formula, it just tells you how many of the element inside the particular material. Silicon, oxygen, there are 1 part of silicon, 2 part of oxygen. If there is 100 silicon, there will be 200 of oxygen. So that's why you might, what we call, this explain why when you see the 3D configuration, there are 1 silicon attached to 4 oxygen, because that's the way how they bond. When you see people talk about silicon dioxide, they refer this lah. But the purpose of they telling you this is because to tell you in general, not in general, in total, there are half of silicon compared to the oxygen. That's what does it mean. Okay, so this is silicon. Let's see something that you normally see before, like diamond, right? So if you want to see a diamond, you just go to the COD here and go to the search, and then diamond is made from what? Diamond. Diamond, what is the element inside? What is inside diamond? Inside diamond, there are only carbon, only carbon. They are only carbon. So we put 1 and 1, and then we send. So we want to find the diamond. We want to compare the structure of diamond and the silicon and how we can infer the knowledge from that lah. So let it, what we call, search the thing. Okay. Okay, so diamond. So let's say, okay, because graphite also carbon. So let me make it more clean, more clear. Because carbon, graphite, for example, pencil. You have pencil? Okay, can I borrow? Imagine this is pencil, real pencil. They are like pencil lead. Even though the name is lead, it's basically not LED is basically a carbon. We call it graphite. Okay. So the reason why when I query for carbon, they can go, they give you graphite, because if pencil lead, inside the pencil lead, there are only carbon also, same like a diamond. So let me go to search first. Go to the carbon. So let's go to carbon, 1, 1. But now let me make it more diamond, diamond, and then we send. We will see later what is the difference between the structure of diamond and graphite. But now we want to compare the structure of diamond and also the silicon dioxide or the silica, the quartz that we see just now. Okay, if you look here, if I take this diamond from here, so you see crystal structure. So let's say I take this, sieve, and then I download the thing. So basically I download, and then I open the file. I try to open the file. Where's the open? Okay, so I rename first. Rename diamond. Okay, enter, and then I click here, and then I open. So you can see this diamond structure. So if you rotate this thing, you can get like this, and then if you go to polyhedral, you will see. So diamond also more or less like the what we call the silicon dioxide, but let me make it bigger. So let me make it like instead of 1, let me 3, 3, 3, apply. Okay, so that is diamond. Okay, so let me close this one and then go to quartz. Let me also make it bigger, just to compare, just like that, 3, 3, 3, apply, and then okay. So you can see this is polyhedral. If you look here, they are like tetrahedral, right? Tetrahedral. It's like a pyramid. Pyramid. The difference between quartz and diamond is that in quartz, they are like a silicon and oxygen. But in diamond, all is carbon. But the most important thing you see is that in diamond, they are more clean, more sort of like compact compared to the quartz. You see, more compact, right? More compact. Compared to the quartz, if you rotate the thing, you see they are like more, sort of like more porous compared to diamond. What we call the way how they arrange in the space is more porous. It's more like, it's not like diamond. It's more like what we call compact, and we can say clean lah. That's why diamond is stronger, is harder than the quartz. But quartz also quite hard, because you see this tetrahedral, when you have something tetrahedral in the formation, that's typically quite hard lah. Quite hard. Okay, so this is diamond and that is quartz. Okay, so if you compare in terms of what we call, if let's say I put here Mohs scale. Previously people okay, so let me put open here. Okay, previously people cannot see, not very clear. Okay, I think you can see lah. Okay, you can see. Nowadays we have like a machine that can measure how hard something is. For example, I want to compare my nail and this this table. Okay, which one is harder? Okay, the way how you test the hardness long time ago is that by scratch test. If you can scratch something, mean that the those that can scratch something, if A can scratch B, A is harder than B. Okay, so if let's say you have something, you try to sort of like take your nail that and then you leave some dent, mean that your nail is harder than the thing. So previously people don't have a machine to methodically measure the hardness of something. They use the Mohs scale. They compare with the back then they know the mineral is hard, so they compare. They give the scale. The diamond is the hardest, 10, and you see the quartz is number 7. It's pretty hard. The reason why quartz is pretty hard because you look at the structure just now. It shares some structure with the diamond, this tetrahedral, but it's not so what we call so compact. So the what we call the least the sort of like the most soft material according to this scale is talcum lah, bedak baby, bedak. Okay, so these are how people back then they compare the hardness of something, and we know that the hardness come from the structure. That's why knowing how the what we call the element or atom configure itself in the space, that's important. Because if you look here, compare this crystallography. Okay, So you might say, okay, this diamond, you compare diamond and quartz. It's not apple and apple because quartz is just silicon and oxygen. Diamond is carbon. Maybe it's not comparing apple and apple. Okay, now we try to compare apple and apple. We compare diamond with the graphite. Graphite also made of the carbon. So imagine this carbon. So graphite is also made from the carbon. So we go to what we call the COD, and then we try to search graphite. Instead of searching for diamond, now we search for C also, 1, and this we put it graphite instead of diamond. So we try to send this into the query, and then it gives you some database. Let me wait for a while. So graphite is like a diamond, contain only carbon inside that, but the arrangement of the atom is totally different lah. Okay, so let's say this what we call. Let's see. Let me go to what? Let me take this lah. This thing. Okay. Okay. Let me take that thing, and then I go to the VESTA, and then I file. I go to open, and then I make a rename here first. Rename, and then let's say graphite. Okay. Enter, and then I open this thing. Open. Okay. So for the diamond, let's say remove the polyhedral, ball and stick only. So graphite is like this. Let me put the boundary. Maybe I put 3, 3, 3, 5, 5 lah. 5, 5, 5. 55. Meaning that the reason why I do this thing is that I want to make it bigger. Okay, that's the reason lah. Maybe I don't want to Z. I don't want lah. Z is 1. So apply. So you can see now the difference between the graphite. So you can see this is graphite, this is diamond. So diamond, every atom connected to another 4 atoms. Carbon, you know, carbon has 4 valence electrons, so carbon want to make a bond with another 4. So in diamond, all atom is sort of like fully occupied because one carbon atom here, you can see here, you can make it bigger. One carbon atom here is basically already combined with another 4. Okay, so yeah, it's messy, right? So that's the thing. But in graphite, you can see the what we call the carbon only connected to 3. Yeah? You see this carbon here connected to 1, 2, 3, compared to diamond. And you see there are no what we call no bond between plane. So we call it plane here. So this is no covalent bond between this. They are only one-to-one bond. So that's make the graphite can slide. That's why when you write with the pen, what left on the paper is this graphite lah, because it can slide. Okay, it can slide. When you write, the thing slide, the carbon plane slide. So that's why you left something on the paper. Okay, and also because of this, there are no bonding here, no covalent bonding between plane. They make graphite has this lubricant properties. Because it can slide, right? So it can make people use graphite to make lubricant. Okay, lubricant here meaning that let's say you have a key, you have the what we call, you have the key like this, you have the key, and then suddenly it's very hard to sort of like open this thing. So what you can do is that you take the pencil, and just take the graphite, just sort of like apa tu, iris apa? Make it sort of like get the graphite. How to what the term? What the term? Ingat easy nak cari term waktu mengajar. What the term? How to, you have something and then you want to shreddy. What the term? I don't know what it is, but basically you make a powder from this, and then you can put inside that, and that act as a lubricant, make it easy for your key to enter the lock, and you can open the key lah. So that is the importance of scrape the pencil lid, the graphite on the pencil lah. So that's you get you put. So that's you can see the same element inside the different material. Same element, carbon, graphite is carbon, diamond also carbon, but then the way how they configure inside the space, will make their properties totally different. Okay, so in graphite they have plane, and in what we call in diamond you have this tetrahedral formation, making it responsible for the extreme hardness of the diamond. So that's important of the, what we call, of the structure, the how atom arranged in the space, okay? Okay, so what you have learned up to now, you have learned that different arrangement of atom in space can influence greatly the properties of the material. So that's the thing that you learned now lah. And also explain how to visualize things in 3D lah. Okay, so from this you may think that the possible number of arrangement of atom in space is infinite. You might think that how come people study this thing methodically if, let's say, if the possible arrangement of the atom in space can be infinite, because if something is infinite, it's hard to study. Normally when you want to study something, it's easier if you can classify or categorize things. But if the possible arrangement of atom in space is infinite, then it's hard. Okay, that is true if, let's say, you talk about non-crystalline. Okay, in non-crystalline material like in glass, if you look here in glass, let's say here, wait, where is the here? For example, in this glass, the possible arrangement is, yes, is infinite. It can be anywhere. But when you're talking about crystal, the possible arrangement is finite. You can classify them based on the pattern. Okay. In fact, you can classify all possible arrangement in crystalline solid in under 7 systems only. We call it 7 crystal system. Let me put, where is the rubber? No rubber. Where is rubber? There's no rubber, no rubber, no rubber, no rubber. Tissue? Anyone have tissue? Duster. What is duster? Duster. Where? Anyone have tissue? Yang satu je, one. Okay, thank you. So basically, the possible arrangement in what we call in crystalline material, people, the people, scientists have categorized under 7 crystal system only. 7 crystal system. And from this, what does it mean crystal system? Jadi that later we will talk about the lattice. But basically, how you can the 7. Let me put here lah. I need to have everything here much easier. Okay, 7 crystal system. Normally they talk about unit cell. I put first unit cell. Later I will explain unit cell. And then from this unit cell here, meaning that, for example, like a cube. So that's basically what does it mean the unit cell lah. I will talk about this detail later. But this, what does it mean by unit cell for timing So inside the unit cell, you can put the atom anywhere. Okay, you can put in the corner, you can put here, you can put here. So there are only 14 ways. 14 ways, 14, we call it 14 Bravais lattice. Okay, so this is one unit cell. This is one type of unit cell. We call it cubic. Okay, we said there are 7. So later you will see 7. Okay, from this 7, you can put the atom in the corner and you can arrange the atom in such a way. So it is unique. So there are 14 ways out of 7 to uniquely put the atom inside this 7 unit cell. And from this 14 Bravais lattice, when you include all the symmetry, you include all the inversion, you include all the what we call the mirror and screw or whatever thing. You don't need to know in detail lah. But what I want you to know is that there are only 230 unique combination of in the crystal. Okay, meaning that what does it mean here is that the number of arrangement of atom in a crystal, they are not infinite. It's finite. Okay. That's cause make people can easily study this thing. Okay, not easy lah, but they allow the crystallographer to sort of like study methodically this thing. Okay, so you have this thing and so on. So let me talk first. Before this, I give a general view first. So in order to understand this, let's talk about the lattice first. About the lattice and unit cell. What is unit cell? Okay, imagine I have this. Imagine I have this. What is lattice? Lattice is basically array lah. Array of point. Array of point. That is lattice. So let's say I have this point. Point. And then there are point. Banyak ni point. Wait lah. Point. This is where I should put that, but it's okay. Point. Okay, so this is the lattice. Lattice is sort of like the framework where you can put the atom. Okay, so inside the lattice, let's say I choose this. Inside I choose this. I can make a vector from here and from here. This is what we call lattice vector. Lattice vector. Lattice vector. This thing, the point here, we call it lattice point. Lattice point. Okay. When you want to make a crystal, what does it mean by crystal? As you can see there, crystal is a material where its atom, molecule, ion arranged in a highly ordered manner. By looking at this lattice, you know that it's already order, right? There are some order here. So normally, remember, this is 2 dimension. We talk about 2 dimension. You can make a square here. You can make a square here. You can make a square here. You can make a square there. So what does it mean, this unit cell? Okay, unit cell is that the smallest, the unit cell is basically smallest repeat unit. Repeat unit. Okay, smallest repeat unit. What does it mean by smallest repeat unit? Is that you can move this unit cell to the next lattice without overlapping or without a gap, leaving a gap. For example, let's say this square, right? This square, I want to move to next. So it will, if I cut this and I stamp here. Okay, so I can create sort of like repeat order lah. And then I take this and move here. So I can repeat that, and by doing that, I can fill the entire lattice without any gap and without any overlapping. Without any gap, without any overlapping. So you see, there are no gap, there are no overlapping. If I repeat this thing entirely, then we have this entire lattice connected with all this square. So this is square lattice. But also you can, there are certain shapes that you cannot make like this. For example, let's say you have a triangle. Let's say I have a triangle here. Triangle here. Okay, I have a triangle here. And then I want to move to the next lattice. What will happen is that you get something like this. If I copy and I paste, I got something like this. There are gaps here. Okay, even though you might say, okay, this is triangle that inverted, right? But lattice doesn't work like that. You need to be the same thing. As if you take this, you stand here. You stand here. Okay, so in this case, triangle is not the lattice system. It's not possible to have a triangle to fill in the entire lattice. Okay, the same triangle to fill in the entire lattice. Because if you make it like this, if you might say that this also triangle, but this triangle is inverted, so it's not the same triangle. So the unit cell is the repeat unit that can fill in the gap, that can fill in the entire lattice without any gap and without any overlapping. That's what does it mean by unit cell. Okay, so triangle is not. Triangle is not. If you have this, let's say, you can also have this. For example, this oblique. Okay, this oblique lattice. This oblique lattice. Okay, this is what we call cubic lattice. Cubic lattice. Not cubic. This is basically square lah. Square lattice. So you can have something like this, parallelogram, and you can also take this and stamp here, and then you can fill the entire lattice. Okay, so this is also one of the unit cell, possible unit cell. In 2 dimensions, there are only 5 possible unit cell. Okay, in 2D, There are only 5 possible unit cell. Unit cell. So we can just go to Google lah. Malas nak tulis. Okay. So Google. Okay. So Google Bravais Lattice. Bravais Lattice. Okay. Bravais Lattice. Okay. So we go to Wiki lah. Our friend Wikipedia. Our best friend. So you can see that. Wait, apa benda tu? Okay, so you can see, you can fill in this lattice without any gap, without any overlapping, if you have this shape only. You have oblique, rectangular, square, hexagonal. Even though they call it hexagonal, but they are distinct. They are oblique. The oblique parallelogram. So this is the only shape that you can put inside any lattice, and they can fit it without any. For example, let's say you see this tile. You see the tile here, your class, the tile here, there are no gap, right? Because they use the square lattice. They learn also crystallography, this thing. Okay. If they use hexagon, they cannot. You might say the hexagon, okay, like honeycomb, right? You say the hexagon here can make like a perfect lattice, but it is not. Why hexagon is not perfect lattice? Let's say, alah, penat jauh tinggi je. Let's say, I don't like dia. Tinggi lah pula. Okay. 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 Okay, it seems like it is sort of like fit everything. But the thing is, if let's say I put the color here, this thing red. And then I put this, what we call, this thing also red, okay? If let's say I want to move this red thing, I just do like this lah, red, to the next lattice point. From here, the next lattice point is here, okay? So you will find like, they are like sort of like something, if you move this to the next lattice point, you sort of like get something, because this is the next lattice point. Okay, you sort of like lift something. It's like overlap. Even though they have hexagonal, they have pattern of hexagonal, but the lattice point is this oblique. Okay, so hexagonal is not one of the what we call the possible unit cell in the 2D. In 2 dimension. Okay. Okay. Okay, so that is in 2D, in 2D. Okay. So this is in 2 dimension. This is in 2 dimension. When you sort of like go to 3 dimension, normally when we talk about crystal, we need to talk in the 3D. So this lattice, this 2D will become 3D. You have X, Y, and then you have a Z at the back on this thing. So when you have 3D, you only have 7. So this is what we call the 7 possible unit cell for the what we call for the 3D lattice, 3D lattice. Okay. So you don't need to remember everything, but you need to know there are 7 types of shapes that when you use this, you can fill all the 3D space without leaving any gap, without overlap. Only these 7. Okay, these 7. 1 on the top, triclinic, monoclinic, orthorhombic, trigonal. Saya boleh baca sini. Tetragonal, hexagonal, hexagonal have rhombohedral and hexagonal, and cubic. Okay, so this is all the possible what we call all 7. 1 top, 2, 3, 4, 5 rhombohedral, 6, and 7. Okay, so there are 7 crystal system. We call it system lah. So that's why I say there are 7 crystal system. Okay, so there are only 7 possible unit cell lah. And then from this 7 system, for example, if let's say you have cube, you have cube, you can put, as I said before, the lattice is just a point, right? You can put the atom there. You can put atom here, atom here, atom here, atom here, or you can put in the middle, here, 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 and so on. Okay? So this is, when you see all the combination, there are only 14. 14 Bravais lattice. 14 Bravais lattice for what we call for this. Okay, you might ask before I go further, why let's so just to tell you about this, why they are center symmetry and so on. If you look here, this picture, the square, there are no center. There are no center here. What does it mean there is that if, let's say, I take this, I take this square. Let's say I take this square. I take this square, and then I put, let's say there are another atom in this middle. Another atom is in this middle. Okay? So meaning that when you have this, you have sort of like another, because it's crystal, they have like symmetry. So you have something like this. Something like that. So even though you have this, but you can create another square here lah. Another square here. Another square here. So it's the same thing. So that's why we don't have the center point for the square. Because if you have center point for the square, you can sort of like translate into the another unit cell lah. So instead of using this as a unit cell, you use this as a unit cell. So that's why there are no center point for the square. But they are center rectangular. You might say, why rectangular here? Why oblique? There are no rectangular. By right, it seems like more or less the same, just this they are in angle right. But why there are no sort of like center there? The reason for that is that if you go here, rectangular lattice, if you look here, okay, so if you look this picture, okay, if you look this picture, we said before, there are no center point for the parallel right, the parallel just now. I saw right just now. But here they are. But when you do this thing, you also can do the rectangular. Faham tak? Tak faham. If you look here, loss you need to focus. Here, if you look here, in rectangular, you have this normal, and then you can put the what you call the center point, meaning that this is unique. Unique. The question is why for the oblique, normal, why there are no sort of like center point for the oblique? If you look this, the difference between oblique and rectangular is just like some is slanted compared to others. But why there are no this thing? The reason for that is because of to avoid the redundancy. Here you can see, even though you have this oblique and then you have the what we call the center point, we put the atom in the center. But normally, like this, you can get this. You can also make the lattice like this. This, normally when we have two choice, we choose the simplest one. Okay, that's why this will be redundant. That's why this is not unique lah. Because you can always have, when you have this thing, what I call parallelogram with the center point, you can always have this rectangle. Okay, here, you can see here, they are parallelogram and they are this in the here. Certain time, people use this. Normally, when you're dealing with the rectangular, this is much more easier than this. Even though this is smaller and the simplest, but in terms of working out, this is more easier. That's why people put this as sort of like one of the unique lattice. Because more often than time, if you can have this rhombohedral, this parallelogram, and this what we call this rectangle with the center point, it's much easier to deal with this than this. I mean, to learn about the symmetry and so on based on this. Okay, so that's the reason why, if you look here, Bravais lattice, there are center points. Something there are center point, something there are no point. So the same thing you can also do for what we call for this 3D lah. We will not deal about why here, and why this thing, but the idea is same as before lah. Okay, so now there are 7 crystal system, and from the 7 crystal system, there are 14 Bravais lattice. What does it mean by 14 is this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So that is 14. 7 system is this: 1, 2, 3, 4, 5, 6, 7. The most symmetric is cubic. You don't need to know all the lattice. 14 Bravais, you don't need to know where is where. But you need to know there are 7. Need to know a little bit lah. Cubic is basically all the side is the same lah. Side is the same and also the angle here is 90 degree. So that is the most symmetric lattice. Okay. So you can see at the bottom here. So for the cubic, where is cubic? For the cubic at the bottom here. So all the side is same. A equal B equal C. This equal 90. So what is this alpha, beta and so stuff, this thing? Siapa ambil ni? Okay, so let me put this thing first. Okay, what is that alpha, beta, and such? That is the notation. When you talk about the lattice, there are notation. Okay, so if let's say I have this, what we call the square. Okay, the square. Okay, the square, and let me, okay, and then I make this as a coordinate. The origin is here. Let's say origin is here. So this is x, not x, this is z. This z, this is x, this is y. Okay, where is A, B, C? So the A here, you can see here, they are A, B, C, right? What is A, B, C? A, B, C is the A, B, C is basically axial line. Meaning the length from here to here. This is A. This is B. And this is C. This is C. Okay? When you see this, what we call the alpha, beta, and gamma, that is interaxial angle. What does it mean? Between A here, for example, between A and Z, this is beta. Okay. Between X and Y, this is gamma. This is gamma. Between Y and Z, this is alpha. Alpha. So this is basically a coordinate system lah. So X, Y, Z is basically coordinate system lah. Coordinate system. So basically when you see the A, B, C, whatever, alpha, beta thing, it's just the way how to talk about the system. Okay, you see what we call the cubic have the most symmetric, yeah? A, B, C is equal. Alpha, beta, gamma also equal 90. The least symmetry is the triclinic. Nothing same. Meaning that A not equal to B, not equal to C. Alpha not equal to beta, not equal to gamma. So that's why you can see here, this triclinic, they just haywire lah. They just what we call, can I click there? So you can see A is not the same with B, B is not the same as C in terms of length. And also this angle is not the same as B. So the triclinic is the least symmetric of the unit cell of all 7, from all 7 things lah. So that's the thing that you need to know lah. And the rest you can play around lah. Okay, the simplest is the cubic, which is what we will focus on. The cubic. Inside this what we call inside the periodic table. If you look periodic table, you might ask how the atom inside the iron only, they fit inside the material. So all the metal, this thing, all the metal, jauh lah. All the metal here, the one that is in color there, metal normally, they assume cubic lattice. And cubic lattice, if you look, we have 3 types of cubic lattice here. We have 3 types of cubic lattice. Let's see here. So you have this, the simple cubic, meaning that all the atoms at the corner, body center cubic, and also face center cubic. Okay, I will show you later on how it looks. But for timing, enough to know, there are what we call, there are 3 types of things. Simple cubic, body center cubic, and also face center cubic. Okay, metal normally cubic lattice or hexagonal lattice. Hexagonal lattice. We will not discuss on hexagonal, but we will talk about the cubic. So let's talk about what is simple cubic. Simple cubic. Okay, simple cubic lattice is like this. Okay, so this is basically a fusion 360. You can draw this thing. Normally when you go for the 3D printing course later on, for example, at the end of this course, week 14, week 13 is about 3D printing. So you need to familiar with the fusion. It's basically you can draw something, anything lah. So in CAD lah, in a computer aided design lah, we call it. So basically this is cubic lattice. If you see the lattice, if you look the lattice, the one that I draw before, 1, 2, 3, 4 in 2 dimensions, I say that this make a square, right? Make a square. When you fill in the atom, you imagine the atom is bigger than this point. This is just a point, lattice point. But imagine you have the atom that is same size. So atom will become bigger, 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 like that. Okay. So you can draw like 4 atoms here of the same size. So maybe like this, like that, like that, like that, like this. Okay. So that is the thing lah. That is the thing in 3D lah. That is the thing in 3D. So the thing, so this is in 3D lah. So this is how the atom is arranged in what we call in simple cubic lattice. Where is the madam? Okay. Okay, I want to show something. How to calculate this. The 2 things that you need to understand with this simple cubic thing, there are 2 terms that you need to familiar, which is the APF. APF stand for atomic packing factor. So how to calculate that is basically volume of the atom divided by volume of the cell. Volume of the cell, you see this cubic. So cubic is the cell lah, is the cell itself. Okay, so let's see. If we have this, if I draw that thing, okay, if I draw like that thing, and then I draw like that, and then I draw sort of, if I draw something like this, something like this, something like this, roughly lah, but something like that lah. And then you have something like this, something like this, something like this, something like this, and then something like this, something like this, something like that. So something like that. Okay. So in order to know the atomic packing factor, what does it mean is that you know this volume of the cell, you know this is A. A, right? A. Because the same A, B, C is the same, the notation. So we can say this A, A. So the volume of the cell, we know is A3. A3. We know it's A3. Now, if you look this atom, this is atom. This atom, if I move it like this, macam ni, it's basically, let's see, put here. So basically they are, let me put here, and it's basically like this. Wait. Okay, so it's something like that actually. I cut it into because remember, we put the atom at the corner, but the unit cell is inside the box, the cubic. So you can see, I put atom in the corner, but then I cut it, that's why I got like this. Okay, so you know this, and this is just what we call, from here to here, mana bini? So from here to here, you know this A here is equivalent, this is R, right, radius. So A equal to 2R. A equal to R. So you can relate A with the R. So volume cell, so we can put this A equal to R lah. So you can relate lah. So A cube equivalent to 2R cube. Like that. So we got volume of the cell. Now volume of the atom. Volume of the atom. We know the atom is a sphere. You see, it's a sphere, hard sphere. And sphere is 4/3. The volume for the sphere is 4/3 pi R3. So this is volume of the sphere. But we need to see how many atoms inside this, what we call this square. How many atoms here? It's not 8. It's Only one atom. Because, macam nak pusing? Okay. So you see, because this can combine with this, combine with this, become the 1/2, and it's as you need to view the atom inside this cube. Okay, they are one atom only. Okay, anyone not clear? Are you not okay? There are only one atom in this cube. If you try to take this and make like a Lego, you can make one atom. That's what does it mean. Okay, so one atom is one sphere. So 4/3 pi r cube lah, times one atom lah, one atom. So you get this and you get this. So you can divide lah. So you can divide that thing. Volume of atom is basically 4/3 pi r3 divided by 8 r cube. Okay, so you can cancel this out, cancel this out, cancel this out. You will get what? You will get this, blah, 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 for 1/6 pi. 1/6 pi, how much is it? 1/6 pi. 1/6 pi, how much is it? Okay, 1 pi/6. How much is it? Pi/6. Hah? Betul ke? 30. Betul? Check. 30 ke? 3 divided by 6. No, this is basically pi/6. Pi is basically 3, right? 3/6 something. How much? 0.5? 5 apa? 0.5? 0.524. What does it mean is that they are 52% lah, roughly 52% that the atom fill the unique cube, this unit. Okay, they are only 52%, meaning that it's not packed enough. They is not packed enough. Okay, so this is so inefficient, inefficient of way of packing, not packed enough. That's why there are only one metal at ambient temperature that have this BCC, which is polonium. If you go to the polonium, if I go here, if I go to crystal and I go to polonium, I search polonium is P, polonium is radioactive, polonium, and then we put 1, 1, and then I send. So they give you blah, 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 blah. So there are only one metal that assume this, what we call this unit cell, because it's so inefficient. Only 52% is filled. So let's say this is polonium. So which one I want to take? Let's say I want to take this one lah. Let's say I want to take this. Okay, and then here, and then I file, open, and then I let's say rename here, rename polonium, enter, and take this thing, and then open. Okay, you get something like this, 3D, and then let's say make it bigger, boundary, let's say I put it 333, 333, apply, okay, you get something like this. But remember, in real life, atom doesn't have a bond. Bond is just the way how you visualize things. But atom, normally, you need to, they are filling the space. It's something like this. Like that. Something like this. Normally atom. The bond is just arbitrary only, just to make it easy to learn. Yeah. So this is actually the thing. Okay. You can see now, this is so ineffective. For example, let's say you have bowling ball, or ping pong ball. You want to stack it. You don't stack like this, right? It's not stable, right? You stack on top of each other just like that. So this is not even stable by itself lah. I mean, if you go in the real life, it's also not stable. So that's why this is so inefficient to the point, if you go to periodic table, crystal, where is our friend, Wiki? Yeah, here. So Wiki. So you can see here, blah, 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 blah. FCC, phase center cubic, FCP, hexagonal, center packing. So you can see polonium, where is polonium? So this simple cubic Okay, even though you may say that, oh, this is also simple cubic, but remember this gas. This gas, they got this structure where they freeze, and then the atom of the oxygen will not move lah. So in ambient temperature, this is gas. Everything here is gas. So you cannot even do the crystal study. They get this crystal study when they sort of like freeze the oxygen to the and become liquid and become frozen. This is not normal lah. But under ambient temperature, the only thing in the periodic element that have this central simple cubic formation as a unit cell is the polonium. This guy, polonium, named due to pollen. So there are history between that also. So there is polonium. So there is polonium. If you look something like steel, something that is normal like this, right? So if I go to CIP and then I go to what we call CIP and I go to the steel made from the, not steel, iron lah. Iron is ferrum lah. Ferrum and then 1 and then I go to sand. Okay. So what is iron? Iron. Okay. Okay, so let's say go to 100. Okay. Let's go the different. Let's see the different. So most of the metal is either face center or body center. Okay. So let's say I take this iron. Let's say I take this. Which one? Which one I want to take? I mean, because when you change the pressure and so on, the structure change a little bit. Okay. So that's why there are a lot of things. Okay. Let's say I take this. Where is the thing? Okay. Let's say I take this lah. Okay. Let's say I take this. Okay, so this is a file open. You can see the different. Open, and this is iron. Iron. Okay, so let's see. I open this thing. So iron is like this. So you can see inside iron, compare with this the what we call the polonium just now. In polonium, there are no atom in the center, but for the iron, there are atom in the center. This is body center cubic. Body center cubic. So example for the simple cubic I put here is polonium. Example for BCC is iron, ferrum. So this example, so if you try to draw like space filling, it become like this. And then if I try to make it more, let's say I put it 3, and then apply. It seems like almost the same, but it's not the same. You see? See here? This is ferrum, this iron, this polonium. Okay? If you don't learn about unit cell, you might see, oh, these two things is more like the same. Okay? Okay? So this is the, what we call, this is iron. Let's see the gold. Gold. So gold, let's say gold here. So I go here, and then I go, gold is our room. Okay, our room. And then I just send. Okay, let's go. Okay, so the gold is example for FCC. Example for FCC is gold. Okay. So the gold. So let's say I go here, sieve, and then I just go to this, and then I file. I open, and then I make a name as a gold. So this is gold. So you see the gold is face center. So you can see the atom is not in the middle, but in the face. Imagine this is the face of the cube, in the face. In the face. Okay, like that. Okay. This thing, if you look in the book, is difficult, but if you try to rotate in the 3D, it's much easier to understand lah. And then I do the space filling. You get something like this, and then let me make a bigger boundary, and then 3, apply. So, okay. So you can see, if for those who don't learn crystallography, they see this thing, and this thing more or less the same, but you know it's different. Okay. And when you try to make, okay, let's go to the iron. Iron is BCC, meaning that it's something like this, BCC. Oh, before that, okay. BCC is okay lah. Where is BCC? BCC. Okay, this BCC. when you talk about the BCC, okay, you can see there are sort of like atom in the middle like that. Okay, so this body center cubic, and also the way how you find the APF also different, a little bit different. You need to play around lah. Don't have time to do that, but I can say for the BCC, the APF, atomic packing factor, is 68. 68 or 62? Normally I show how, but I'm afraid there are no time. 68%. 68%. So you can see the way how you pack using the BCC is much more efficient than BCC. Okay, much more efficient than the simple cubic. Okay, so this color is not good lah. I think I need to put the blue color so that you can see. So for BCC, the APF is basically 68%, and for the FCC, so this is BCC. For FCC, face center cubic is like this. Okay, like that. So that is the BCC. So this is BCC. So you can see it's more packed. Okay. So FCC, so this is FCC, face center cubic. So the APF for this is 74%. This is the most efficient packing possible in anything. 74% lah in the unit cell. Hexagonal lattice, also like the FCC, the APF is 74%. So this is maximum packing lah. One thing that you need to know apart from the APF, when you talk about this thing, you need to know also about coordination number. Coordination number. Okay. Coordination number is that how many atoms that touching this. For example, let's say I thought the simple cubic, simple cubic coordination. So if you look here, this picture, what is this picture? Okay, this picture, you can see this is what we call the simple cubic, simple cubic. But instead of making it, mana? I can see here, rupanya. Here, if you see simple cubic, if I put one at the top, one at the side, one at the top, and then I put one in the front and like that, you get this thing. You get something like this. Just to show you that one atom touching, one atom here, there, in the yellow, that touching 1, 2, 3, 4, 5, 6 atoms. So meaning that in this what you call, in this polonium, one atom of polonium will touch 6 other polonium atoms. So that is coordination number. How many atoms they touch lah. So coordination number for the SC, simple cubic coordination number is 6. Okay. Okay. So how many atoms touch with each other lah. Okay. So if you look here, so that is the thing. For the body center cubic, you can see easily from this picture lah. Okay. One atom touching 1, 2, 3, 4, 5, 6, 7, 8. Okay. So it's much more packed. That's why it's more packed, because one atom they have neighbors. There are a lot more neighbors. Okay. So for this thing, for the BCC, green is not good for writing. So for this thing, BCC, for the coordination number is 8. Okay. For the simple cubic, coordination number is 6. And from the for the FCC, face center cubic, if you look here, face center cubic, if I draw like this, okay, so it's basically just, so that, the one that I showed you before is just 1, okay, 1, but I want to show you how the atom touch each other lah. Because if I just show you only one like this, like this, it's hard to see this atom touch how much, because it's not full atom, it's not like a ball. So that's why I add one more, so you see something like Mana? So you see something like this lah. I make it up, copy and make it up lah. So you can see that one atom there in the middle, the full atom like a sphere, they touch 1, 2, how many? So 1, 2, 3, 4 at the bottom. Okay, 1, 2, 3, 4 in the middle, and 1, 2, 3, 4 and the top. So if you look there, so it's touching lah, touching. Okay, touching there. So this, try to draw yourself lah, because you will learn a lot more how you do it one time, you draw by yourself, and then you remember forever. Okay. So this is the what we call this the coordination line number and APF. The reason why we learn this is because we want to see what is the most, what we call most efficient packing. Okay, and you can see the APF for this coordination number. Let me add before I forget. So the coordination number for this, is 12. 4, 4, 4, 12. The coordination number for this also 12. So you can see the more packed, the more efficient the packing, the more numbers of atoms neighboring another atom. Okay, that's why it's more packed. So that's why the reason people learn this, do this, all these things, to know the theoretical density of certain material. For example, if you go to Wikipedia, they tell you the density, right? The theoretical density can be calculated based on this lah. Okay, so how to generate the APF is like this lah. Volume of atom versus volume of cell, and this I show only for the simple cubic. I don't have time to show about the BCC and FCC. If you want to know that, then you can just come to my office and I will tell you lah. So this is the sort of like the basis of crystallography. You need to know about the unit cell, because from the unit cell you know where to put the atom. Once you know the atom, where to put the atom, you can sort of like see whether it's efficient packing or not. And the reason why people get this, okay, last, the reason why people know the diamond have this configuration, the reason why people know the diamond have this configuration is because of the SRD. Okay, you have done the experiment of SRD. I think I don't have time to explain about that in detail, but the idea is that you shine the SRD, the SRD will give the pattern, and from that pattern you can sort of like back calculate backward to get this thing. Okay, and yeah, the BCC, SC, and also the FCC here, simple cubic, base center cubic, face center cubic, is basically the most easiest lah. The most easiest. Remember, this only the cubic system. There are like 7, right? So we only focus on this because this is what the metal like this, how the atom inside this metal sit. So when you see this metal like that, this metal, so this metal might have different arrangement than this metal. I mean the way how the atom arranged in the space. So that is crystallography. And you know at the beginning, from the beginning we said that knowing the structure, how the atom arranged in the space can influence the properties. Okay, like what we call like the diamond versus the graphite. The way how they arrange in the space will influence the properties. So that's why this is important. This is the fundamental part lah. So I think that's it for crystallography.